Okay, 7.4 rational exponents. So the big idea here is going to be that we're going to talk about another way to write radical expressions, another way to write rational expressions. All right, and a rational expression is something with a root. So what we're going to use here is we're going to say, well, we'll say the nth root of x is equal to x to the 1 over n, right? So that n, that index, went into the denominator, okay? A note that we need to write here is that this is, well, here, this is radical form, and this is exponential form. Right. The note that we need to say here is that exponential form always indicates principal root, indicates principal, always indicates principal root. So we're always going to be talking about the positive root there, right? The easy root, the root that you would normally think about. So let's look at this in context here. Number one, here we are going to be simplifying. So we have 125 to the 1/3. We're supposed to simplify that as much as we can. So that 1/3 in the exponent, we could write that as a radical. That would be the third root of 125, which we know is 5. All right. Next up, let's look at number 2. We could have 10 to the 1/4 times 100 to the 1/4. So these, we could rewrite these as the fourth root of 10 times the fourth root of 100, which gives us the fourth root of, what is that, 1,000? 1,000. Now, if we were to break that up, we'd find that we wouldn't be able to simplify that anymore. That's as simple as it can get. So we could either write it as the fourth root of 1,000, or we could return it to exponential form and say this is 1,000 to the 1/4. Right? Either of those would be a good simplification. All right. Here we have a new idea. We're going to talk about rational exponents. So this takes what I already said at the beginning and it kind of puts it on a little bit more steroids, right? So we have a to the 1 over n is the nth root of a, right? That's already what I've written down, right? Actually, I think I used an x. Next up, we can say that a to the m over n is the nth root of a to the m. Or we could also say this is equal to the nth root of a, all of that to the m. In our theorem, we're supposed to have the caveat that we have to say the nth root of a is real, and then we're also supposed to say that m is integer. M is the exponent there, right? So you can't have a decimal in your fraction, is what that's trying to say. Yeah. So we're going to use this idea next. So let's look at number 3 here. Number 3, we're going to say we have x to the 3/5. And our directions say write in radical form. So we're supposed to write in radical form. That is really terrible handwriting. That's okay. So writing in radical form, we know that the 5 in the denominator there means that we're talking about the 5th root. So I'm going to have the 5th root of x, and then that 3 in the exponent can go right there. And we could either write it like that, or we could write it like that, where the 3 is outside and cubes the root. You could either have it inside the root or outside the root. It's the same thing. All right, moving on. Number 4. Number 4. We're going to say, this says, write in exponential form. We have the square root of a cubed. Right, let me write that again, that 3. There we are. Well, we have a square root. It might be beneficial to put a little 2 there to show that that's the square root that we're talking about. We know that the index, the number that we're rooting, right, that index, that goes in the denominator of the exponent. So this is going to turn into a to the 3 over 2. And there we are. That's it. Let's look at number 5. Number 5, we're going to have the cubed root of x squared. And we're supposed to, again, write it in exponential form. One way that I think is sometimes helpful to do here is, what if we write our exponent as a fraction to begin with? Sometimes that's useful. In this one, it probably wouldn't matter, but sometimes later on it will. So we'd still have the cubed root of x, but now it's to the 2 over 1, right? Because it's a fraction there. And then we can say, well, this is x to the 2 over 1 times 1 over 3, right? This is my exponent, this is my root, and then together this makes x to the 2 over 3. And that's our answer. Sometimes it's beneficial to break it up like that. In this one, it probably wouldn't have mattered, though. All right, number 6, we're going to talk about root 5y, right? The 5 and the y are underneath the root. So this is a square root. One thing that's going to be useful here is, let's put parentheses around the 5 and the y, right? Right now, they're unneeded parentheses. But whenever we change this, it's going to be 5y to the 1/2. Now there's a common, and this is the answer. There's a common mistake here. A lot of people will want to write 5y to the 1/2. But what we're really doing there, that would be equal to 5 root y, which is not what we originally had, right? You have to make sure that the exponent there that represents the root goes to everything that was under the root, right? So this 1/2 goes to the 5 and the y, whereas this 1/2 only goes to the y. So this here is our correct answer. This is not good. All right, next up, we're going to have a bunch of properties of rational exponents. So properties of rational exponents. All right, if you wrote nothing down so far, this next piece is something that we need to write down. We need to assume M in are rational and assume all denominators are not equal to 0. Okay, those are assumptions that we normally would have if we see a fraction, right? Normally you just think of it as, well, the denominator is not 0, but we want to make sure that we write it. So our first formula, idea, whatever we want to call it, we're going to say a to the m times a to the n is equal to a to the m plus n, right? That might be something that we've already gone over before. Then we're going to have a to the m to the n. Well, that's equal to a to the m n, where you multiply them. Next up, we'll have a times b to the m. That's a to the m, b to the m. This next one might be something new for you. We have a to the negative m is equal to 1 over a to the positive m, right? The way that I like to think about that is that exponents don't like to be negative, and you need to put them in the place that they belong, right? They're not happy if they are negative, so you need to flip them over the equal sign, over the fraction bar. Next up, we have a to the m over a to the n. That is equal to a to the m minus n. And to finish off, we're going to say a over b to the m is equal to a to the m over b to the m. All right. These are all very good things to know and to remember. A lot of these are going to kind of, later on you'll think the formulas are kind of silly and we don't need those. So some things that some examples of these. Starting off with our top green one, a to the m times a to the n. All right, let's say that we have 8 to the 1/3 times 8 to the 2/3. Well, our formula tells us that we can add our exponents. So this is going to be 8 to the 1/3 plus 2/3. Well, that's 8 to the 3/3, which is 8 to the, which is 8 to the 1, which is just plain old 8. That's a way that we could use that. Next up, say we have something like 5 to the 1/2 to the, I don't know, 2/3. We'll say 2/3. Well, if we have that, if we have an exponent, parenthesis exponent, you multiply them. So this is going to be 5 to the 1/2 times 2/3. So this is going to be, we could cancel out our 2's, and it's going to be 5 to the 1/3. And that's as far as we're going to go. Next up, let's say we have 4 times 5 to the 1/2. Well, this would be the same thing as 4 to the 1/2, 5 to the 1/2. Well, we know that 4 to the 1/2 is really the square root of 4, right? So this is going to be 2 times 5 to the 1/2. Next up, say we have 9 to the negative 1/2. Well, that's the same thing as 1 over 9 to the 1/2, which is the square root of 9, so 1 over 3. Right? It's sometimes useful to write in your fraction here and say that, well, it's 9 to the negative 1/2 over 1. Sometimes it's useful to do that. Next up, we'll say, let me move this down just a little bit. Say that we have 5 to the m, not 5 to the m, we'll do 5 to the 5th over 5 to the 4th. Well, this is 5 to the 5th minus 5 to the 4th. Oops, excuse me. 5 to the 5 minus 4, I'm sorry, which is 5 to the 1, which is just plain old 5. Now we could look at this original statement there, and you could write out all those 5's, and you could cancel them out on top and bottom and get the same answer. This is just kind of the faster way of writing them all out and canceling them, right? This is basically just canceling things over a fraction bar, only it's written a little bit fancier. And that last one, I think we know that before, or I think we've gone over that before. But say this is like 2/3 squared. This is the same thing as 2 squared over 3 squared, which is 4/9, right? These are very important to have. I think this would be a good thing to have a note card of. Make sure that you have these written somewhere. So moving on, let's do example number 7. We're going to say we have 25 to the negative 3/2. Well, for starters, I want to make the exponent happy, right? It's negative, so it's uncomfortable. This is the same thing as 25 over 1, right? So I'm going to flip it over the fraction bar. So I have 1 over 25 to the 3/2. The exponent is now positive. So this is the same thing as 1 over the square root of 25 cubed, which is 1 over 5 cubed, which is 1 over 125. All right. Last example, number 8. We're going to say we have 8x to the 16th, and then parentheses around everything to the negative 1/3. So for starters, what I'm going to do is I'm going to split our, I'm going to distribute this exponent here. So splitting up our parentheses. So this is 8 to the negative 1/3, x to the, it's going to be negative 16 over 3. Right? If you have an exponent, parenthesis, exponent, you multiply them. So this is the same thing as, I'm just going to flip them over and put them both on the bottom. This is going to be 1 over 8 to the 1/3. And then we're going to have, what are we going to have? X to the negative 16, not negative, positive, excuse me, 16/3. Well, what is 8 to the 1/3? That's the cubed root of 8, which is 2. So we're going to have 2, and then we have the cubed root of x to the 16th. Now we're going to need to simplify the x to the 16th. How many sets of 3 x's are in there, right? Well, the cubed root of x to the 15th would be x to the 5th, right? So we're going to pull 5 x's out, and then 1 x is left in. So we're going to say we have 1 over 2 x to the 5th cubed root of x. Like before, we have to rationalize our denominator. So I need to figure out how many more x's do I need to get rid of my root completely. Well, I need a set of 3, and I only have 1 in there, so I'm going to multiply by x squared still to make it a set of 3. So whenever that happens, I'm going to end up with a cubed root of x squared on top. On the bottom, I'm going to have a 2, and then this turns into a single x, and then I have an x to the 5th, so this will be an x to the 6th. And there's my answer. All right. Again, it would be a very good idea to have this stuff written down somewhere. All right. That's all.